In this video, we're going to have a look at something called the central limit theorem. Now, many people, when they do statistical tests, especially those involving means, they get very hung up on the assumption of normality. And the basic idea behind the assumption of normality is that many tests, especially when testing differences between means, assume that the sampling distribution of means is normal. So what people tend to do is look at their sample data, see whether their sample data are normal. If their sample data are normal, they assume their population data are normal too. Now, the central limit theorem is interesting because it basically says that if your sample size is big enough, then means will be distributed normally anyway, regardless of what your original population looks like. So essentially it means that if we have a big enough sample, we don't need to worry about whether our data are normally distributed, because the means from the population that we've sampled will be normally distributed regardless. So it's a bit of a weird thing to get your head around. So to illustrate it, we're going to have a look at an example. So the example we're going to look at is how many blows to the head it takes to kill a zombie. Now, the best way to kill a zombie is, well, if you've got a shotgun handy, is to shoot it in the head. But especially in the UK, we don't tend to own shotguns. You'd have to do with something else. So any kind of blunt instrument that you have is a potential weapon against a zombie. And if you want to take out a zombie, then aim for the head. That's the thing to do. So we might have a kind of a population of zombies, and we might, within that population, know how many blows to the head it would take to kill them. So, does it generally take one blow to the head, or 2 blows, 3 blows, or whatever? Now, what we can do is generate some artificial data to illustrate this. Now, to begin with, what I'm going to do is generate a population of data. This is based on 100,000 zombies, and the data represent how many blows to the head it took to kill them. So first of all, let's generate that sample of data. So by executing the bit of code that I just have, all it's doing is it's creating 100,000 numbers that are going to represent what we're interested in looking at. So having generated those data, we can have a look at what the distribution looks like. So you can see in this graph here, this is just a histogram of the population data that we just generated. So basically you can see that the bars are all the same height, and all that means is that each score within the population is equally represented. So you can see we've got a number of blows to the head to kill a zombie. The minimum it takes is 1 blow, so one very forceful blow, you can kill a zombie. But in some cases, the more resilient zombies may take 2, 3, 4, 5, or the maximum value that we have is 7 blows to the head. So you can see the distribution is completely flat, which just means that any value between 1 and 7 is equally likely to occur. So if we were to randomly sample a zombie from our population, it will be equally likely that it was killed with 7 blows to the head as it would 3 blows to the head, or 4 or 5 or 6. So any of those values between 1 and 7 are equally represented in the population. So this population distribution is absolutely not normal. It's what's known as a uniform distribution. So any value within the population is equally likely to occur as any other value, and that's illustrated nicely by that histogram. Now, what we can do to illustrate the central limit theorem is to take samples from this population. Now, this mimics what scientists do all the time. We take a small sample of people or whatever it is we're interested in, and we use that sample to try and generalize to a population, or to tell us something about the population. For example, to estimate the mean of the population. So this bit of code that I'm highlighting here, basically that represents the idea of sampling. So I'm using a function here that takes a sample from the population data. So our population contains 100,000 numbers, and what this is going to do is it's going to take 30 values from that population. So, and it's gonna store them in something that I've very usefully called X, because I couldn't think of anything better to call it, really. So if we execute that, you can see, and I'm displaying it on the screen here, we get a sample of 30 cases of data. So this is just like going into our population of 100,000 numbers and plucking out 30 of them randomly. So you can see within our sample we've got a zombie who took 5 blows to the head to kill, the second zombie only took 1, the third zombie was killed in a single blow, and our fourth and fifth zombies took 3 blows and 5 blows respectively. So we've got 30 zombies in our sample. And what we can also do is calculate the mean of that sample. So we can see here that sample, on average, it took 3.86 blows to the head to kill zombies within that sample. So that's just one sample from the population. Now what would happen if we took another one? So we can just repeat this process, use the same function as before, but now notice that we get a different sample. So the numbers have changed, we've got different zombies to the ones before, but they come from the same population. Now again, we could calculate the mean of this sample. And you'll notice it's slightly different. It's around the same value because, after all, they're from the same population, but it is slightly different. So our mean here is 3.43. Now we could do this again, and, well, I'm sure you get the gist here. We've got a different sample of zombies now. So we've got different numbers or different amounts of blows to the head that it took to kill them all. And again, we could calculate the average of that sample, and again we find it's a slightly different value to the other two. Now this is what sampling is all about, taking a small group from a bigger population and then working out some kind of parameter. In this case we're looking at the mean. Now the question is, what would happen if we did this lots and lots and lots and lots of times? Now, you know, you don't, as a scientist, you don't do this in real life, but we can emulate what we could do hypothetically by taking lots and lots and lots of samples. So what I'm going to do is I'm going to create basically a bucket where I'm going to store our samples, and then I'm going to take lots and lots and lots and lots of different samples. Now what this bit of code here is doing is it's doing exactly the same as I've just done before. So each time before I ran a little thing that took a sample out of the population and then I calculated the mean. It's just doing that again. So it's taking a sample, calculating the mean, and then it's saving that mean, and then it's taking another sample and then saving the mean, and then taking a different sample and saving the mean. What it's going to do is it's going to do it 5,000 times, and it's going to do it very quickly indeed. So what we're doing is we're taking 5,000 samples from the same population, and in each sample we're calculating the mean value. So if we do that pretty quickly, it's done already, which is fairly outstanding. What we should have now is a bunch of sample means. Now you can see it's a very long list here, but this is the data that we've just stored. So this is, you can see, well, we've got thousands of samples, and in each sample, when we took it, we calculated the mean. So this column of data here is just mean values taken from different samples. So the mean value for the 3,436th sample that we took. If we scroll right to the top, then, oh, that takes a long time. The first sample that we took had a mean of 4.08, the second sample 4.10, third sample 4.44, and so on and so forth. Until, because we've got 5,000 samples, we end up with our last sample, our 5,000th sample, gives us 3.7 as a mean. Now what happens if we plot a histogram of these sample means? So this is a histogram of the 5,000 sample means that we've just computed. Well, interestingly, you can see what happens. You get what looks like a very beautiful normal distribution. So remember, our original distribution was not normal at all. It was completely uniform. It was an incredibly non-normal distribution. But the sample means, if we were to resample from that population lots and lots of times and plot the distribution of those means, then we get a normal distribution. Now, bearing in mind, the samples that we were taking were samples of around 50, actually. So we were taking samples of 50 people. That's a 50 zombies. That's a reasonably big sample. Now, just to illustrate, just how normal this looks, we can also plot a density plot rather than a histogram, and you can see you get the nice, relatively characteristic bell-shaped curve. So it's not perfectly normal, but if you took an infinite number of samples, what you'd find is that curve would become closer and closer and closer to being perfectly normally distributed. This is what the central limit theorem basically says. It says that no matter what your population distribution looks like, no matter what it looks like, can look like anything, if you sample and if you take means of samples an infinite number of times, they will be normally distributed. Now we're going to illustrate this with a second example. So this time we're going to recreate a new population that is not going to be uniform, but instead is going to have a slightly different distribution. So here we have it. This is our population, and I've actually generated this using a chi-square distribution. So this, well, you can see it's a very sort of skewed kind of distribution, where essentially what this would basically tell us is that the most frequent number of blows to the head to kill a zombie is actually just one blow. So a single blow is on balance enough to take out most zombies. And at the other end of the curve, there's only relatively few zombies in the population where it took 7 blows to the head to kill them. So most zombies are killed with 1 or 2 blows to the head, and then the number of zombies requiring more blows to the head is going down and down and down as the number of blows increases. So this is the kind of distribution you might see in social science data. It's incredibly skewed because you've got high frequencies of values at the low end. So again, if we go through this whole process of resample, I mean, if you looked at this, you would probably not expect that if you took lots of samples and then calculated the means that the distribution of those means would be normal. But again, we can do the same process as before to simulate this. So again, we've taken 5,000 samples, and each time we take a sample, we calculate the mean. So we end up with 5,000 means, and we can look at the distribution of those means just as we did before. So the whole process I'm going through is exactly the same as before, and you can see, again, even though our distribution started off incredibly skewed and weird and non-normal, when we plot the sample means based on 5,000 samples, we get something approximating a normal distribution. And if we took an infinite number of samples, it would become more normal. And again, if we look at the density plot of this, that shows again, how we're starting to approximate a normal curve. So that's the central limit theorem. It just says no matter what your population looks like, it can be uniform, it can be exponential, it can be a chi-square distribution. No matter what it looks like, if your sample size is big enough, then any means that you calculate based on that population are going to follow a normal distribution. So what this effectively means is that when we use relatively large samples in research, we should be obsessing a lot less about what the population looks like, because we know, based on the central limit theorem, that the means that we calculate in our samples should follow an approximate normal distribution.